yours, please, Miguel.
Okay. Thanks for the invitation. And okay, this is the workshop on combinatorics, number theory, and dynamical systems. So my plan for the talk is to give you 3 results, one in combinatorics, one in number theory, and one in dynamical systems. And the point is that these results are easy to understand. And so maybe in this way, everybody can find something of some interest in the talk. Or maybe not. And okay, so the results are easy. The ideas, I think, are also easy to understand. And of course, I will not get into much detail in any of these results, but if any one of you is interested, I will be very happy to discuss these things lately. So okay. So these results may appear to have not much in common, but actually all of them exhibit a phenomenon that I like very much, which has to do with this idea of discrete algebraic structures. And the phenomenon is as follows. In many problems in these areas, it is very usual that what one wants to show is that the object one is interested in behaves in a random manner, behaves like one will expect probabilistically. So it's very usual that you have a very interesting object and you want to show that this behaves in a random manner. So, of course, in general, it is easy to show that most objects behave in a random manner, but it may be very difficult anyway to prove that the precise object that you're interested in behaves in this random manner, or maybe that all objects behave in this way. So it is a remarkable phenomenon that many breakthroughs have been made in these areas lately, which goes as follows. You show that actually the only way in which an object can fail to behave in this random manner, the only way an object can behave very different from how one will expect from a random object is if it possesses some specific kind of algebraic structure. So this appears in many contexts in different problems in these areas, and it is particularly useful because if you think about it, these problems are hard. I mean, showing that a specific object behaves in a random manner can be very hard because for these problems, you don't know why this should be true. You expect this to be true because it's what usually happens, and there is no reason why it should not happen in this particular case. But if you think about it, this is giving you no reason to attack your problem. It's just what you will expect randomly. So the idea of finding this algebraic structure is that then you can say, well, if the only way an object can behave very different from random is to possess some specific kind of algebraic structure, then I can simply show that my object does not have this specific algebraic structure and then conclude the random behavior of this object. So this will be a common theme for the 3 results I'm going to talk about. So let me begin with the results in dynamical systems that will be in the study of non-conventional ergodic averages. This is something Mate was mentioning in his talk previously. So the context is as follows. This is a result in ergodic theory. So X mu is any probability space. You're given T, T1, TL, measure preserving transformations of your space. And for this discussion, we will always assume our functions to be bounded. So this is the context we need. Any probability space, any set of measure preserving transformations, and any set of bounded functions. So non-conventional ergodic averages is what we want to study. So we consider probably the most basic result in ergodic theory, which is von Neumann's mean ergodic theorem. This result says that if you take the classical ergodic averages, so you take one function and one transformation and you make the averages along the orbit, then these things always converge in the L to norm. So let me remark that I'm making the assumption that my functions are always in L infinity because that is the right context in which you can make the general conjectures I'm going to talk about. So von Neumann's theorem says that the classical ergodic averages always converge in the L to norm. So we want to understand to what extent this result can be generalized when dealing with several transformations and several functions. So how much of this holds in this greater generality? So we seek to generalize this result. And there are many ways in which we can do this. There are many ways. We have many functions and many transformations, so we can play with them in many different ways. So for example, a very basic thing we can do, probably not terribly interesting, but still, is to consider iterations of this transformation. So you're given one function, you have several transformations, and instead of just applying one to your function, you first go n times through one orbit, then n times to another orbit, and so on for L different orbits. So this is a very basic way in which you can combine these different transformations, but maybe not terribly interesting. More interesting, perhaps, is to consider multiple functions. So here you take L functions and you take L transformations, and you study the average when for each function you go along a specific orbit. So for each function you take an orbit of your choice and you want to study the behavior of these averages. So this is interesting because many problems in number theory can be formulated about correlations and functions, and this is exactly what we are asking here. We want to understand how these functions correlate with each other. And many problems in number theory can be expressed in this way in combinatorics. The obvious example here is that Semerides theorem can be stated as that the limit of this is positive in a specific case. So this is multiple functions, and another thing we can do is say, why should we just go linearly? Instead, we can replace this exponent here by just any polynomial. So, of course, we cannot take any arbitrary function up there, because if we do that, then we can just simply make this behave as bad as we want, and we will not have the conversions we are going to discuss. But you want some kind of function that actually has the sufficiently structure as to preserve the rigidity of your problem. And polynomial functions play a role here. This is what something of Vitaly was telling us on Monday, that you have to believe in polynomiality. So it is this polynomial structure that actually preserves the kind of rigidity we need in order to guarantee the conversions of averages. So this is all the different kind of things that you can do with averages. And of course, you can combine any of these. You can take multiple functions and make many iterations and take polynomials. These are just different directions. And so what we want to know is we want something like von Neumann's theorem. Von Neumann's theorem tells us that conversions holds for any bounded function. So what we want is, we look at the group generated by the transformations, and we want to know what conditions we have to impose on this group to guarantee that all these averages always converge in the L2 norm for every choice of bounded functions. What is the condition the group of transformations has to satisfy to guarantee conversions? And the result is that, in fact, conversions always holds as long as the group is nilpotent. So let me read you the statement. Let G be a nilpotent group of measure-preserving transformations of your probability space. Then these general averages, which can be strange to understand the first time you see them, but it's just all the possible combinations you can make with what was in the previous slide. So you can take any iterations you want, you can take as many functions as you want, and the polynomials depend both on the function and the transformation, so you have complete freedom in your choice. So all these combinations that you can make will always converge in the L2 norm as long as the group is nilpotent. So this always converges for every set of transformations in your group, every choice of bounded functions, and every choice of polynomials, integer-valued polynomials. So this result, the study of these things dates back to the 70s, the work of Furstenberg. He advertised the conjecture of conversions of these things, and already in a paper of Bertelson some time ago, it appears the conjecture in the case of abelian groups, and this precise conjecture, as it is stated here, appears in a paper of Bertelson and Liebman. So let me tell you some work towards this conjecture. So maybe a very well-known result is due to Host and Kra, with a different proof subsequently found by Zikla. And it says that if you take these averages, conversions holds for every choice of function. So notice that in this average you have one fixed transformation and you go along an arithmetic progression. So this result is particularly interesting because this is the average that corresponds to Semerides theorem. But that is not the only thing of interest of this work. In fact, what is very interesting is that Host and Kra give a description of the limit in terms of inverse limits of nil systems, and this is very important in applications. So it is really a very interesting result of Host and Kra, different proof by Ziegler. Let me say that, okay, the case of two transformations here was dealt by in the work of Furstenberg, and then there is also work of Consol and Singh. And in general, the case when you just have one transformation, that is the case of bicyclic group, was the only case of the conjecture that was known in full generality. So, okay. So another interesting result is due to Furstenberg and Weiss. They show that if you take these averages where you go linearly along the first function and you go along the squares in the second function, then this always converges in the L2 norm for every choice of bounded functions. And this is very interesting because for two reasons. The first one is that it is the first nonlinear result. It was the first nonlinear result. But also because it is the first time in the literature where the concept of a characteristic factor is formally introduced. And this concept plays a very important role lately in ergodic theory. And although in our proof we will not need the idea of characteristic factors, one can see these characteristic factors as the infinitary reflection of the kind of discrete structure, the algebraic structure that I'm going to talk about. So this is the result by Furstenberg and Weiss, and let me say that when the group is abelian and the transformations weakly mix in, Bergelson had already proved conversions in that case. So this is another result, so maybe you can wonder why nilpotent group? I mean, maybe this seems like a very strange assumption to make. In fact, let me tell you that it is a necessary assumption. So let me give you this result of Bergelson and Leibman, who say that if you consider the simplest possible non-conventional ergodic average, so you just take two transformations with two functions and you go linearly, the simplest possible non-conventional ergodic average, then these things converge in L2 if T1 and T2 generate a nilpotent group, but they do not necessarily converge if they only generate a solvable group. In fact, the literature show that if your group has exponential growth, you can always find a pair of transformations such that this does not converge. So again, the assumption of nilpotency has a lot to do with this idea of algebraic structure, because if you look at the literature, you can realize that there is a strong connection between dealing with nilpotent groups and preserving algebraic structure. Let's say, probably the first result that may come to your mind is Gromot's theorem. It tells you that virtual nilpotent groups are precisely those with polynomial growth. You can also look at, for example, in Lindenstrauss' talk, it was mentioned, he talked about Rander's theorem, which makes the assumption of unipotency on the generators, which is essentially the same thing as dealing with nilpotent groups, and it's essentially for the same purpose, trying to preserve the polynomiality of the behavior of the orbits. And also this result of Broglie, Green, and Tao answering qualitatively a conjecture of Helfgott and Lindenstrauss that says that approximate groups are actually controlled by nilpotent things. So when you deal with this kind of linear or polynomial things, it is usually the case that this structure is preserved as long as you are inside a nilpotent group. You can think that if your group grows faster than nilpotent, faster than polynomial, then you will lose this polynomial structure. So there's a very strong connection between the condition of polynomiality and of nilpotent groups. So, okay, so you see that even if you take the simplest possible ergodic average, non-conventional ergodic average, you do not get conversions for solvable groups. And let me mention this result of Tao because it is the most important from the point of view of the proof. It says that if your group is abelian and the polynomials are linear, then conversions always holds. And this is very important for us because it is the first time that different methods were used. Here, it was the first work where the concept of characteristic factor was not used and instead replaced by finitary methods. And although our proof does not use finitary methods, it does use discrete ideas that are very much inspired by this point of view. So let me say that there is also a lot of other interesting work. As I said, the case of cyclic groups was completely settled by Hoskra and Liebman. And there was also more recent result by Franzikinakis, Host and Xu, where they showed conversions in the abelian case and polynomials of different degrees. And also the result of Tim Austin, who established particular cases, but he actually manages to give a lot of information about the limit of these averages. So maybe if you want to find out about what the limit looks like, you will need to use this kind of ideas. So anyway, so this is again the result, conversions of all the general averages that you can make always hold as long as the group is nilpotent. And as I said, I will not get into much detail in the proof. I will just give you some very rough ideas. And so first let me give you this sketch of how the proof goes. So the first step is very classical. It starts with Furstenberg himself, and the particular ideas we use are due to Gowers, a very beautiful geometric idea of Gowers, about how to decompose a function into a structured part and a random part. So it is usually the case that your random part behaves very nicely. So in general problems, you look at a function, you decompose it into a structured part, a random part, the random part behaves nicely, so you can get rid of it. And then you're just left with the structure, but of course you have to understand what is the relevant structure in your specific problem. So in this particular problem, it turns out that you can define a notion of structure that accomplishes the following. If you apply a transformation to your structure function, it will be so rigid that it will actually look like a simpler system. So you start with any function.
So it looks like what?
The structure part, when you apply the transformation, say you apply a quadratic transformation, then it looks like something simpler. It may look like applying something linear. So the strategy is clear. You start with a function. You decompose it into the structure and the random part. The random part behaves nicely. You can take that away. The structure part looks like working in a simpler system. And then, of course, all you have to do is find a suitable induction to reduce the problem to a trivial case. So take the random part away. The structure part looks simpler. You make an induction. That's the strategy of the proof. Yes. So you start with one of these functions. You make the decomposition. The random part is so nice that makes everything go away. And then the structure part behaves simpler here, and then you have to, in turn, deal with each function. So again, I will not give you much detail, but I want to say something about what the structure is, very rough idea, because there is where this idea of algebraic structures appear. So the concept is called reducibility. So suppose, take this particular example. Just consider this example which has all the features. So suppose we are given commuting transformations T1 and T2 and two bounded functions. Then you can take these averages where you go along the squares in one case and linearly in the other case. And you want to see that this converges. And of course, what you want to do is to realize what is the right definition of structure in your problem. But of course, it will be very strange that somebody will look at this and come up with the idea of what the structure is. On the other hand, it is remarkable that we have very good intuition for what random is. And the whole idea of this is that the concept of structure and the concept of randomness should be dual to each other, should be the opposite to each other. So the reasoning is clear. You have good intuition for randomness, so you want to know what happens if this behaves in an opposite way as to a random thing. So what happens is, say, F1 is random. Well, again, we have some kind of intuition. If something is random, it should oscillate so widely that it has to produce cancellation in your sum. That will be something that one will naturally expect of a random function, behave so widely as to produce cancellation. So if F1 is a random function, then, for example, this is a simpler context, but it has the same ideas. If F1 behaves randomly, then we will expect that, for example, the integral of these averages should go to 0. F1 should behave so widely that there is no way that something so structured as, going along the squares here and going along another orbit linearly could possibly catch the behavior of F1. So if F1 behaves randomly, we will expect this to go to 0. So we now make the opposite questions. What happens if this does not go to 0? So we want to understand the opposite behavior. We want to see what the right notion of structure should be. So suppose that, in fact, this is bounded away from 0, is greater than some epsilon, for some finite but large value of n. So some value of n so large that you will not expect this to be for a random function. So what does this imply about F1? So, okay, you will have to take me somewhat on faith on the following calculations.
So you assume that F1 has 0 integral, right?
Well, that will be a consequence of being random. If it behaves randomly, the probability of being is equal of being positive or negative, so it has integral 0. So if this does not behave randomly, if the integral is greater than some epsilon, then we must have that F1, these are indeed easy calculations in this case I'm talking about, F1 should look like this average over here. So again, this does not seem to be very useful, but if you think about it, this is very nice that you have replaced one function by an average of several functions. Averages of things tend to behave much nicer than just one specific object. In particular, we can do this kind of Vanderkopper trick here. So F1 will look like a very large average. This is a very large value of n. So if you take a very small value of h and you move this a little, this will not change much. So you're making an average in a box of size n, a very large value of n, and then what you do is apply just a small h. So what you're doing is moving the box a very little, so the average will not change much. So in the end, what this is telling you is that the definition of structure is related with some kind of invariance property. So if F1 was a structure, it will look like this, and this has this kind of invariance properties, at least for h much smaller than n. So a particular consequence of this, if you believe me, is that, for example, if you apply T1 to the h squared to F1, then h squared only appears here. So in fact, this gets canceled out. So a consequence of this invariance in this particular case is that T1 h squared of F1 will behave like a linear average. So you have something quadratic that suddenly behaves linearly. In particular, the whole system will behave linearly, because this was the only thing nonlinear. And so this will behave linearly for small values of h. So again, you got this structure for some large value of n, and you deduce information for small scales. And this is one place where this, here you have this kind of algebraic rigidity where you can reduce things. This is, in general, the advantage of having polynomial things is that this kind of reasoning reduces to simpler algebraic things. And in particular, it's very relevant here that you are using discrete algebraic things, in the sense that, again, h is much smaller than n. And what you're doing is you go to a very large value of n, and you take information there, and you go back to your small scales. You can do this because it is possible to get these decompositions that I talked about before at different scales. This is a nice consequence of many approaches, but in particular, you can see it very nice when you think geometrically in the way of Gauer's article. So a very nice consequence is that you can make decompositions where you have one part that is very structured. For example, here corresponds to a very large value of n, while the other part is random at another different scale. So whatever this means, the thing I want to point out is that here you have taken a lot of advantage of the fact that you're working in a discrete way, that you can go to a large value of n and then go back to small scales. The same reasoning working in the infinitary context directly will fail. You actually reduce this to conversions in another case, but actually this kind of uniform discrete conversions. That just conversions is not enough in this case. Yes?
What do you mean by T1 h squared? Because if we use the T1 h squared, then we still have the n squared. That doesn't.
Well, but the point is that actually n will be fixed. So you go to a large value of n, you deduce this for some fixed value of n, and then you work at small scales. And for small scales, this is fixed. So in the end, what you have is a large but finite sum of linear things, right? For each n, you're summing each one of these, and each one of these behaves linearly in h. So you're changing the parameter. Yes. So you take this information for a large value of n, but then you actually work in the scale of h. So then you lose this nonlinear behavior. And in this way, this multi-scale analysis allows you to recover information that otherwise would have been lost in the limit. Okay, so this is one nice application of this kind of weak inverse theorems, where you actually show that opposite behavior from randomness implies some kind of structure that actually allows you to get progress on your problem. So that's about all I want to say about this problem. So let me switch to another problem where this kind of dichotomy is more evident. So this is a problem I like very much. It's called the inversive problem. And it has to do with as follows. Take this notation, n to the d is just the first n integers to the d. And of course, a central problem in number theory is to understand the distributions of sets in residue classes. So of special sets in residue classes. For example, today Janos talked about what we know about primes in residue classes. Also, it was Harald's talk. And of course, this is not just an interesting question, as Janos was pointing out. It also has applications. It's one of the main tools we have to understand the distribution of sets of primes, for example, in residue classes, the Bombieri-Vinogradov theorem, or Zhang's result, which improves on this Bombieri-Vinogradov theorem, and that allows you to get bounded gaps between primes. So it's not just an interesting question, but actually it's very much like, knowing how a set behaves in each residue class is very much like knowing the Fourier coefficients of a function, right? So it's something that's very useful in applications, a very interesting phenomenon. And of course, not just primes. I mean, there are a lot of things you care in analytic number theory, for example, how they distribute in residue classes. For example, how do varieties distribute in residue classes? If you, in the case of algebraic curves, for example, knowing good estimates for the number of points mod p is the Riemann hypothesis over finite fields. In general, it's the Lang-Bailey inequality. These are very natural equations in number theory, understanding the distribution of sets in residue classes. So again, we have this thing. We usually want to show that the specific object we are interested in behaves very well in residue classes. And in fact, you can show that if you take a random set, it will be well distributed in the residue classes. Most sets are well distributed. In fact, we expect a random set to occupy essentially all the residue classes mod p. So this is again a phenomenon where the usual behavior is what you really want to show in your specific problem. So in fact, if you think about it, for example, if you ask, if you want to know what kind of sets occupy few residue classes mod p for many primes p, if you think about it, it is very unlikely that a set will occupy few residue classes mod p for many primes p, because that it will be badly distributed, because there are just a lot of primes. So it is unlikely that for each prime your set will be badly distributed. So that would be a strange behavior, but actually that happens very often. So there are certainly examples of very badly distributed sets. You can take, for example, the set of squares. Then it is very well known that S, so you take the squares, 1, 4, 9, 16, 25. It is very well known that S occupies only p plus 1 over 2 residue classes mod p for every odd prime p. So the squares occupy only half the residue classes for each prime, which again is something very strange, but it happens. And if you go to higher dimensions, then you get more trivial examples. For example, you can consider in 2 dimensions and consider just the diagonal. The first coordinate equals the second coordinate. Then in 2 dimensions, you have p possibilities for the first coordinate, p possibilities for the second coordinate. So you have in total p to the square possible residue classes. And if you take the diagonal, then you're just occupying p of these p square possible residue classes. So in fact, this is a trivial set that occupies very few residue classes. And more generally, you know that the solution set of any polynomial equation of low degree occupies few residue classes mod p for many primes p, for most primes p. This is the precise estimate is the Lang-Bailey inequality. So you see there are a lot of sets that are badly distributed in residue classes. But evidently, if you look at it, they have some kind of common feature. They are very algebraic, maybe in different ways. This is the image of a polynomial. This is the solution set of a polynomial. So again, the study of the distribution of things in residue classes is a very classical topic in analytic number theory, let's say. And still, you have this interesting phenomenon where all the examples you can come up of things that are really badly distributed in the residue classes are kind of a very specific form. So it is a very remarkable conjecture that was put forward not so long ago that goes as follows, the inversive problem. So it reads as follows. Take any set that occupies few residue classes mod p for many primes p. And let me make 2 remarks. You can replace occupy few residue classes by just saying that it is badly distributed in the L2 norm. So it is just a particular case. So this is just to simplify. And of course, I only consider primes because once I know, for example, that it occupies few residue classes for the primes, I know it occupies few residue classes for every integer. So suppose you have a set that occupies few residue classes mod p for many primes p, then actually there are just 2 options. So either your set is small, so if you have a very small set, it is rather trivial that for most primes it will occupy few classes just because it is small. So if you make a reduction, it will be small. So either it is for a rather trivial reason, or your set has to have some kind of algebraic structure. So again, I very much like this question because you have this classical topic, distribution in residue classes, and you find out that actually there is a complete classification of things that behave very badly in distributed classes. There has to be a reason why something has to behave badly in residue classes. It has to have some kind of algebraic structure. But there is a problem with this statement, and it is that C theory already tells you that your set has to be somewhat small. So maybe saying this is not really very strong. On the other hand, what does algebraic mean? If you think any set is algebraic, if you take, you're dealing with finite problems. So any finite set is the solution of a polynomial equation of sufficiently high degree, so this question may seem meaningless. So this is not the real conjecture. The real conjecture is this one. If S occupies few residue classes mod P for many primes P, then either S is very small, it is much smaller than what you already knew, or it is very algebraic. Not only you have a polynomial, say, vanished on the set, but actually you can get a very strong bound on the degree of this polynomial, the coefficients of this polynomial. So this is the problem. This conjecture was formulated in full generality by Helfgott and Venkatesh, and in a particular case, it was also formulated by Krut and Elshotz. And, okay, as I said, sieve theory shows that S cannot be too large. And what is known by now, for example, is we have this result. When d equals 1, and under additional hypothesis, recent results of Ben Green, later refined by Sean Bourgain, and later refined again by Ben Green and Adam Harper, imply that S must be very small. So what this additional hypothesis look like is that you assume your set has some kind of structure that is very different from algebraic structure. So you assume your set behaves very differently from how an algebraic set will behave, and you conclude that in fact your set has to be very small. This is the kind of results that you have here. But still, this result still does not manifest this kind of dichotomy where you actually show that there is some algebraic structure if the set behaves badly. In that regard, the result known was due to Helfgott and Venkatesh, who actually proved that this conjecture holds when d equals 2. So actually, there are two forms of this conjecture. There's one form that it has to do with images of polynomials that I will not discuss, that corresponds only to the case d equals 1. And there's another conjecture that corresponds mainly to d greater than 1, which says that your set has to be the solution set of some polynomial equation. So Helfgott and Venkatesh actually show that when d equals 2, you have this dichotomy. Either the set is small or it has to be very algebraic. So, and in this case, the d equal 1 case follows from work of Gallagher. So d equal 1 Gallagher and d equal 2 is this result of Helfgott and Venkatesh. And so the next result I want to say something about is that this holds for every dimension. So in fact, so the conjecture holds for every d greater than 1. In d equal 1, there is another phenomenon that we still don't understand. But you have this general statement. So let me read you the general statement. Let k and d be integers, and let epsilon and eta be two parameters. Then there is some constant c that depends only on these parameters, such that for every set that occupies less than a constant time p to the k residue classes for every prime p, so for every set occupying few residue classes for every prime p, at least one of the following holds. Either S is small, so this saves a power over what was known, or otherwise S is strongly algebraic. There exists a non-zero polynomial of degree at most c, so uniformly bounded degree, and coefficients bounded by n to the c that vanishes on almost all your set. Remember that you choose eta here. So in fact, the only way a set can be badly distributed in residue classes is for it either to be very small or to be strongly algebraic. And let me remark that this result is optimal. This is the best possible bound because there are sets that have this size and do not satisfy the second condition. So this is the optimal, the best possible result. So this settles the inversive problem for every d greater than 1. So let me leave you again a very quick sketch of how the proof goes that has common features with a lot of problems that have been solved recently. Yes? Of course.
So for d equals 2,
yes.
then k is, say k is equal to 1,
yes.
then S has to be either bounded or...
yes, S has to be either less than n to the epsilon, will be in that case, or lie in a curve. Yes. Yeah.
Equal to 2 was already
Helfgott and Venkatesh result, yes. So yes, when d equals 1, this reduces to Gallagher's, to the consequent of Gallagher's work. D equals 2, the result of Helfgott and Venkatesh, and then you have this result for arbitrary values of k and d. And okay, so this is this result. And how the proof goes is that whatever generic means, you show that if your set is nice, it's just generic, then you can find a very small set inside your whole set, a very small set, such that if a polynomial vanishes at this small set, it automatically vanishes at your whole set. So this is also a common feature in this kind of discrete algebraic problems, that the whole structure of your set is controlled by just a few number of points. So, and the reason for this, okay, an impression of what the reason is that because your set occupies very few residual classes, your points are all very connected, mod p for many primes p. So you have a lot of connection between your points. So you can actually reduce the behavior of the whole set to just a few number of points. And, okay, second step will be to show that if your set is very large, this is not very different from what Josh was talking about on Monday, that this kind of extremal problems, right? If your set is very big, it necessarily has to emerge this kind of structure. So if your set is, in this case, if your set is very big, what you actually show is that you have so many points that you can remove the ugly ones and show and reduce things to a generic set. So if you have a very large set, you can actually cut things off to get a nice generic set, so that in particular you can find a small set A, such that this happens. And then once you have a small set A, you just build the polynomial by hand. So you show that if your set, if you have a few points, such that if a polynomial vanishes there, it vanishes the whole space. And then if the set is very small, you can simply build your polynomial by hand, any small set that meets a small polynomial vanishing there. And okay, that's how the proof goes. And if you look at it, you can say this is the a version of the polynomial method. Yes? What? Well, uniformly bounded. Yes, really, really small. So for any set that is badly distributed, you can control it with just a finite number of points that is uniformly bounded. Yes. And this idea of reducing things to smaller sets and then finding a polynomial vanishing there, I found out this happens in a lot of places, and it's called, in general, the polynomial method. You can see this way back, for example, in results from the transcendental number theory, for example, Baker's theorems. Or you can see it in the work of, for example, De Vere's solution of the Kakeya problem over finite fields, also uses the polynomial method. And then there is this algebraic topology methods for the Euclidean case. And, well, and the Erdos distance problem on combinatorics. This is something that is appearing in many different places lately. So, okay, so let me tell you here very quickly give you an idea of how this, I said this is optimal, so there are sets that are badly distributed and are big. Let me give you a brief idea of how these sets look like.
You cannot have the union of both of a small set with the algebraic set?
Well, yes, one of the two happens, maybe both of them do. What you can guarantee is that your set either is small or is strongly algebraic. Of course, you can build strongly algebraic sets that are very small.
No, but you cannot have the union of a strongly algebraic set which is not small with a small set which is not strongly algebraic.
In general, in all these results, it is usually the case that you can always add a small amount of things and don't change things, so you always have this small error. Yes? Yes. Okay, so how do these examples look? This is just a quick idea. So Chinese remainder theorem, very basic thing, tells you that you can build very badly distributed sets occupying less than p to the epsilon residual classes that are very small. As I said, if you have a very small set, you know that it is badly distributed. So you can construct sets of logarithmic size occupying only p to the epsilon residual classes mod p for your prime p. In particular, if you consider this set, for example, where in the first coordinate you take anything you want. So it is already big because the first coordinate is anything you want. And the other coordinates, you restrict them to these special sets. Then you have p possible residual classes here, all of them, because it's anything you want. You have only p to the epsilon possibilities here and only p to the epsilon possibilities here. And of course, then this will occupy only p to 1 plus 2 epsilon classes, which is very small, but the set is very big. So this is a trivial example of something that is big and badly distributed. So when you look at it, you say, well, this is not really a problem because I know why this is failing. I can just say that the problem is that the set has small sections. But that's not the only kind of example you can build. You can take two polynomials f and g, and then you can consider this. You take x in the first coordinate, And polynomials have the property that once you know the class mod P of x, you automatically know the class of f of x mod P. So you have the class of x mod P. This fixes the class of f of x and g of x. And then the only variation is given by y and z, which again only occupy few residue classes. So anyway, this is another way of constructing a badly distributed set. But this also has some kind of algebraic structure because you are perturbing something that is very algebraic. You are multiplying something that is very algebraic. But this, again, is not the only example. You can make things even worse. You can take a large union of polynomials, take a large set of polynomials, a large set of these things, and take the union of all these things. And if you make these things, these combinations in a clever way, you can also show that these will be big sets occupying few residue classes. So you can actually have a lot of ways to construct badly distributed sets. But and you can take subsets of this, and so it can get very ugly. But as it turns out, it is very difficult to make things more ugly than this, uglier than this. And in fact, that's something, okay, that maybe you cannot do worse than this is an observation made or question asked by Ben Green. And this is another result, which is maybe much more general than the other. Because if you look at this result, although it is an optimal result, it is very annoying that small is actually this power. Maybe this is not that small. It's a sharp result, but, well, what can you do if the result is sharp? But it still may be annoying. As it turns out, you have this result. If you take any set occupying less to the p to the kappa residue classes for every prime p, here kappa is any real number less than t, any set that is ill-distributed, then you can always find some non-zero polynomial of degree at most log n to this exponent, vanishing on almost all the points of your set. So this is, here you don't need any assumption of size. So any set occupying few residue classes mod p for many primes p, then necessarily there has to exist some polynomial of logarithmic degree vanishing at almost all your set. So it is the only way a set can be badly distributed in residue classes, is essentially to be the solution set of a polynomial of logarithmic degree. Okay, so for integer values of k, that something like this should hold was constructed by Green, and as the previous example showed, you cannot do much better than this because you can in fact construct things of logarithmic size as before. So nothing better than a power of a logarithm is possible here, but you always get that for any set occupying few classes. And the last result, well, I will be much briefer about the last result because actually maybe it has less connections to what I've been hearing in the conference so far. So if you think about it, all these methods are about building algebraic, finding algebraic structure. So that leads you to a very basic and natural question in mathematics, which is to understand quantitatively how do things that are very algebraic behave. So we go back to one of the most basic questions in number theory, which is to estimate the number of small rational solutions of a polynomial equation. How many small rational solutions can a polynomial equation have? And in particular, as all these ideas are very important, the uniformity in the estimates, that they don't depend on the specific curve or set. So we want estimates for the number of rational solutions of an equation that are uniform over the choice of function. So equivalently, let's see, being an irreducible projective curve of degree d, what we want to know is uniform bounds for the number of integer points of height less than n on such a curve. So how many points of height at most n can a curve have? So recall that for an integer, if you have, this is your integer point, then the height is simply, if you write this in primitive form, then the height is simply the maximal size of a coefficient here. So small solutions. Okay. So of course there is a lot of literature on this, but it is well known, you want uniform estimates, it is well known that if you take a genus zero curve, a rational curve of degree d, the number of points on this curve grows like n to the 2 over d. So the number of rational points grows like n to the 2 over d. Consider, for example, x minus y to the d. You can see that it grows, the number of rational points grows like n to the 2 over d. So this is well known, but the implicit constant here depends on the specific curve. So for each curve you know this, but the constant depends on the curve, so it can be you can possibly you can always find a curve such that there are too many points because the implicit constant is big. Okay, so you know that you cannot get a bound that is better than n to the 2 over d. You know that there are curves that grow like n to the 2 over d, so you want a uniform bound, it cannot be better than n to the 2 over d. So the question is it true that for every irreducible projective curve of degree d, you can always, you have this estimate that the number of points is less than a constant that depends on d times n to the 2 over d, where the constant is independent of the specific curve of the specific equation. So it is true that there are most a constant time n to the 2 over d points on a rational curve with a constant independent of the curve. It will be the uniform, the best possible uniform estimate. And so the last result I will mention quickly is that, in fact, this is true. It's okay. So, okay, let me tell you what was known. A very well-known result of Heath-Brown tells you that for every epsilon greater than 0, you in fact have this estimate for the number of rational points on a curve, uniform estimate. So the number of points is less than n to the 2 over d plus epsilon, where the constant here depends on d and epsilon. So this is a very strong bound. But the problem, of course, is that as epsilon goes to 0, this constant here goes to infinity. So still, you have infinitely many more points that you will expect, but it's still a very sharp estimate. So this work of Heath-Brown uses what is called the p-adic determinant method, and is inspired by the corresponding work of Bombier and Pili in the fine case. So it's a very strong bound. Now, the sharp estimate that I was talking about before, n to the 2 over d, was obtained by Browning and Heath-Brown in the case of when the degree equals 2, and that was the only case in which it was known, degree equal 2. And more recently, it was proven by Rold that it holds for singular rational curves satisfying some additional assumptions on the resultant and discriminant. Another relevant work in this problem that I'm not mentioning are due to Broberg, Marmon, and Chong. Other results with some assumptions on the curve, but uniform estimates. But for the result I'm going to mention, the most important results are the following. Ellenberg and Venkatesh, they actually show a very strong result that says that notices the following. Your polynomial is homogeneous. So if the coefficients of your polynomial are big, your polynomial will take a larger scale of values. So it is much more unlikely that it will actually be 0. So the largest the coefficients of your form are, the less the number of points one expects the curve to have. And they prove a result of that kind, and they use that to obtain this uniform estimate for curves of geometric genus at least 1. So in particular, you have a power saving over the bound for curves of geometric genus at least 1. Of course, for example, geometric genus at least 2, you have faulting theorem, and which of course tells you that the number of points is finite, but the constant, the number of points, depends on the specific curve. So you remember that you're dealing with a finitary problem, so it is not very useful to know that it's just finite because it will be your whole space, because your whole space is finite. So what you want is uniform estimates. So they actually show that you can have a power saving over the bound for rational curves in the case of geometric genus at least 1. So it's a very strong result. And the other result that is very important to us is due to Saarberger. He developed this global determinant method that will not say anything about what this is, but tell you that he used this to solve a conjecture of Serre on the number of points on varieties, on algebraic varieties. So it's a very nice method. And he employed this method to this problem to get the estimate that the number of points is at most a constant times n to the 2 over d times log n. So again, this is not a sharp estimate, but it's also a very strong bound that holds uniformly over all curves, but still, because of this log n, the quantity can be much larger than infinitely many times what one expects. So this was the best known result on this problem. So the last result is that, in fact, you have the optimal bound. So there exists an absolute constant independent of the specific curve, such that for all irreducible projective curves of degree d, the number of points on the curve is at most this constant times n to the 2 over d. And as I showed you before, this is the optimal, the best possible bound, because you can make curves to grow like that. So there are at most a constant time n to the 2 over d points on an irreducible projective curve of degree d. And as I said, a crucial ingredient, but not ingredient because we actually use different methods, but an important inspiration for the proof is the result of Ellenberg and Venkatesh, that the estimates become better the larger the coefficients of the form are. So in fact, we have the following result. So take any primitive because it's necessary, you have to scale, otherwise it will be false, primitive, irreducible, homogeneous polynomial of degree d, then the number of points on this curve is at most n to the 2 over d times this factor here. Here, this is the size of the largest coefficient of f. So it is at most the bound I said before times log of f divided a power of f. So of course you always win. The power always beats the logarithm. So, but this, when the coefficients are large, is a much better estimate. So in particular, this implies this result here, that the number of points is at most a constant time n to the 2 over d. So this is the last slide. This result is deduced from a result for general hypersurfaces. So again, here I'm working, my discussion, I'm making it for plane curves, but actually the result holds in any dimension, a curve in any dimension. It does not have to be in 2 dimensions. And in fact, all this is deduced from a result for hypersurfaces. So the result for hypersurfaces tells you that if you have any primitive, irreducible, homogeneous polynomial of degree d in any number of variables, then you can always find an auxiliary polynomial g that vanishes of degree at most this. So this is some power, that's some specific power, and here you have this saving over the coefficients. This auxiliary polynomial, not divisible by f, that vanishes at every rational point of x. So you have your specific function, your solution set, you can always find another polynomial of very controlled degree that vanishes on the points of small height of your original polynomial. So in particular, if you take this with 3 variables and you apply the Suits theorem, this implies the bound for the number of points that I mentioned before. And then you can make a projection argument and use this for in any dimension, for curves in any dimension. So the proof includes Sahlberger's global determinant method that I mentioned before, but it is used in a different way. In particular, the way we use it is we combine it with a result of Bombieri and Baller on the size of integer solutions to linear systems of equations over the integers. Combining these two things, you can actually get this kind of bounds, but I will not get into any detail about this. So anyway, let me finish here and hope you could find something of interest in some part of the talk. Thank you.
Are there any questions or comments?
Just to try to understand